Hey, Lance here, and I've talked a lot on this channel about the decline in NAD+ levels as we age, and about how taking NAD precursors like NMN or NR can help to restore those lost NAD+ levels. But today, I'm going to be talking about an intervention that might be able to prevent that loss in the first place. So stick around. I'll be right back. Today, we're going to be talking about CD38, which is probably the molecule that contributes the most to the loss of NAD+ as we age. While NAD+ can be used in a lot of different processes in the body, nothing uses it up like CD38. In fact, it uses so much that if we could prevent the loss of NAD+ by CD38 alone, if that was the only thing that we did, it's likely that we could maintain our NAD+ levels as we age. So with that in mind, we'll also be talking about interventions that you can do to inhibit CD38 and the loss of NAD+. Let's start with an explanation of what CD38 is. CD38 is what's called a glycoprotein, and it's found on the surface of many of our immune cells. The CD stands for cluster of differentiation, which is a protocol that's used in the identification and phenotyping of cell surface molecules. CD38 was first discovered as a surface marker for several immune cells, such as T-cell lymphocytes, monocytes, B cells, and natural killer cells. But it was also found to be an activator of both B cells and T cells. But CD38 is also known as cyclic ADP ribose hydrolase. Now, a hydrolase is simply an enzyme that acts as a catalyst to break down chemical bonds using water, also known as hydrolysis. And it's in this role as an enzyme that we're going to be talking about CD38. ADP stands for adenosine diphosphate, and it's what ATP, adenosine triphosphate, converts into when it gives up a phosphate atom. ATP, you'll remember, is the universal energy source for all the cells in our body, and is created in the mitochondria of our cells. CD38 is considered to be an NADase. According to this paper, an NADase is an enzymatic process that leads to the degradation of NAD. CD38, in addition to being a cell surface marker, is also an enzyme that catalyzes the synthesis of both ADP ribose and cyclic ADP ribose from molecules of NAD+. And it uses 100 molecules of NAD+ to generate a single molecule of cyclic ADP ribose. Now, let me repeat that. CD38 requires 100 molecules of NAD+ to create just one molecule of cyclic ADP ribose. So let's talk for a minute about NAD+. Nicotinamide adenine dinucleotide, also known as NAD, is a transport molecule that has a couple of states, NAD+ and NADH. As it transports electrons, drops them off, and then goes back for more, it's constantly bouncing between these two states. Now, NAD is a derivative of vitamin B3, or niacin, and it's used in over 500 enzymatic reactions. It's present in every living cell on Earth, and it's critical to our survival. Let's talk about some of the processes that use NAD+. So first off, NAD+ is used in cellular respiration, which is the process that creates ATP, the universal energy source. It's also used as fuel for our sirtuins, also known as the longevity genes. Sirtuins are used in regulating many of the functions that influence the aging process. They regulate mitochondrial biogenesis, they stimulate apoptosis, they inhibit inflammation, and they stimulate chemical signaling at the cellular level. NAD+ also activates PARPs, which are a family of proteins involved in a number of cellular processes, such as DNA repair, genomic stability, and programmed cell death. And of course, NAD+ is used by CD38 in creating cyclic ADP ribose. Now, as we age, our levels of NAD+ go into decline. We create less and less of it. With our diminishing supplies of NAD+, we get reduced levels of ATP production, reduced levels of ongoing DNA repair, and lower levels of sirtuins, all of which we need, and the loss of which leads to aging. Declining levels of NAD+ is one of the big pathways that leads to aging, and it's considered by many to be a leading cause of aging. And it has a big impact on the hallmarks of aging. It can impact genomic instability, deregulated nutrient sensing, mitochondrial dysfunction, cellular senescence, and altered cellular communication. So why do NAD+ levels go into decline as we age? Why does it appear to get all used up? If we look at the levels of sirtuins and PARPs, they seem to mirror the declining levels of NAD+. When NAD+ levels go down, so do the levels of sirtuins and PARPs. And when levels of NAD+ rise, the levels of sirtuins and PARPs rise right along with them. So declining levels of NAD+ seem to cause declining levels of sirtuins and PARPs, rather than the other way around. But as we age and NAD+ levels go down, CD38 levels rise. More and more of it is produced. In fact, the rise in CD38 levels seems to be a reflection of the lowering of NAD+ levels. So it looks like the rise in the levels of CD38 is the cause of declining levels of NAD+. And this has been proven in mice models. When researchers inhibited the production of CD38 in mice, the mice were able to maintain their levels of NAD+ as they aged. Over the course of their lives, with CD38 production inhibited, they showed no signs of diminishing NAD+ levels. Which raises the question, why is CD38 produced in such large quantities as we age? Well, one way that CD38 is produced is that it's secreted as an SASP by senescent cells. SASPs are senescent-associated secretory phenotypes, and they're highly inflammatory. And our load of senescent cells increases drastically as we age. Now, there's a study that shows that this inflammatory effect is worsened by NAD+. So it's thought that CD38 is secreted in order to lessen the inflammatory heightening effect of NAD+ on SASPs. Okay, so we've demonstrated that the decline in NAD+ is probably caused by rising levels of CD38. Now, some interventions have been developed to replace that lost NAD+, to restore NAD+ to youthful levels. I've talked extensively on this channel about NAD+ precursors like NMN and NR. Both of these have been demonstrated in numerous studies to raise levels of NAD+. But what if we were able to prevent the loss of NAD+ in the first place? What if we could inhibit CD38 and prevent it from using up all the NAD+? Because it's thought that CD38 is secreted as an SASP, one way to inhibit CD38 might be to clear out senescent cells through the use of a senolytic agent, like fisetin, quercetin, or dasatinib. Now, we don't want to block all the CD38. That's been tried, and that didn't work out so well. Scientists have developed molecules that can completely block all CD38 production, but in studies, it turned out that these molecules caused disordered osteoclast formation and function, it altered airway responsiveness, it impaired immune response, and it both inhibited contraction of the aorta and caused cardiac hypertrophy. So you don't want to block CD38, you just want to inhibit it and prevent CD38 levels from rising as you age. And it turns out that by both taking NAD+ precursors on the one hand and inhibiting CD38 on the other, these two interventions combined have the most beneficial effect on aging NAD+ levels. Okay, so what are the most effective CD38 inhibitors? Turns out it's apigenin and quercetin, and they're both polyphenols. Polyphenols are naturally occurring pigments that give fruits and vegetables their bright colors. So the study that I was referring to earlier showed that both apigenin and quercetin inhibited CD38. These two graphs show that as doses of both apigenin and quercetin increase along the bottom, CD38 activity decreases. But does decreased CD38 activity result in increased NAD+ levels? Yeah, it does. According to the paper, CD38 inhibition by quercetin and apigenin increases NAD+ levels in cells. These graphs show that for both apigenin and quercetin, as CD38 activity decreases more with higher doses, NAD+ levels go up. So do these graphs. Now we're looking at NAD+ levels for WT, or wild-type mice, as opposed to mice that have been bred so that their CD38 has been genetically knocked out. As you can see, apigenin raised NAD+ levels 75% higher than the control, while quercetin only raised them about 30%. So let's take a look at apigenin and quercetin one at a time. Apigenin is a polyphenol that's found primarily in parsley and chamomile, but also in red wine, beer, celery, artichokes, and oregano. In fact, apigenin is one of the most widely distributed polyphenols in the plant kingdom. And studies seem to indicate that using the dried forms of these plants provide the most apigenin. Dried parsley contains about 130 to 140 milligrams per gram, compared to about 13 to 15 milligrams per gram of apigenin in fresh parsley. That's about 10 times as much apigenin in dried parsley as in fresh parsley. So using either dried parsley or steeping dried chamomile as a tea are the most common ways of ingesting apigenin. However, there are some storage and bioavailability issues with apigenin. First off, it's unstable if stored long-term at room temperature, so it needs to be stored below minus 20 degrees centigrade or minus 5 degrees Fahrenheit. It has low solubility in water and it has low bioavailability. As it turns out, your gut health is a big factor in the bioavailability of apigenin. The bacteria in our gut can break down the larger apigenin molecules into smaller molecules called glycoside conjugates, and these are more soluble in water than apigenin is. And it's been found that apigenin that's bound to beta-glycoside is the one that's the most bioavailable. So, how much apigenin do you need to take? A study found that between 3 and 10 milligrams per kilogram were required. Now, that's a pretty big range. For me, that's between 275 milligrams and 900 milligrams per day. Now, I've heard of people taking up to 1 gram of apigenin daily, and that's in the upper range of what's required for my weight. So I'm thinking that if I take between 750 and 1,000 milligrams per day, or between 0.75 and 1 gram, that should be enough. Now, I've mentioned earlier that dried parsley is a good source of apigenin, but at 130 milligrams per gram, I'd need to eat about 7 to 8 grams of dried parsley every day to get 1 gram of apigenin. I found that it's a lot easier to simply take an apigenin supplement rather than eat so much dried parsley. Okay, let's move on to quercetin. As I mentioned earlier, it's also a polyphenol. Quercetin can be found in apples, honey, raspberries, red onions, red grapes, cherries, citrus fruits, and leafy vegetables. However, just as with apigenin, quercetin has bioavailability issues. And just as with apigenin, quercetin that's in the form of glycosides appears to be more bioavailable. And that's how most quercetin appears in nature. Bromelain, which is a protein-digesting enzyme extracted from pineapple, can improve the absorption of quercetin, as can vitamin C. A study published in 2019 estimated that only 20% of the administered dose reached the blood. But this same study found that when quercetin is combined with phospholipids into quercetin phytosome, it can be 20 times more absorbable. So I've heard of people taking anywhere between 500 milligrams and 1 gram a day of quercetin, but I don't know if that's quercetin phytosome. I found a number of sources for quercetin phytosome, and they all recommend taking between 1 and 2 servings of 250 milligrams each a day. Now, there's a lot of sources out there for both apigenin and quercetin, but if I may, I'd like to recommend Do Not Age. They have high-quality products, and I verified that their apigenin is bound to beta-glycoside. Now, I've discovered that Do Not Age doesn't use quercetin phytosome, but they've assured me that their quercetin is just as bioavailable as quercetin phytosome when consumed properly, which would be taken with a meal. I've included links in the description to their products, along with a code to get a 5% discount. All right, that wraps up this video about inhibiting CD38 to maintain NAD+ levels as we age. If you would like more info on NAD+, then watch this playlist right here. That's it for me. I'll catch you guys next week.